Okay, what we're going to do now is a seemingly unrelated thing, and we're going to be doing Newton's law of universal gravitation. So much writing that didn't even bother finishing all those words. So what is the universal law of gravitation? It is the way we measure gravity. But Mr. Keeney, gravity is always 9.8. Yeah, but no. Over very long distances. Emphasis on the very. Okay, so this is how we calculate the forces of gravity between like the planets and fun stuff like that. Alright, so let's jump in. We're going to talk about how the pieces are related before we just give you the formula, because then it will be more meaningful, hopefully. So the first thing is mass. Let's imagine you've got two things around. You've got the person that's sitting nearby to you, not too close, of course, because you're socially distancing and all that, and the Earth. Okay, so here is you. You're standing here. You're happy. You. Which one are you going to be more attracted to? Spoiler alert, it's the Earth. Alright? Why is that? Because more mass means that you have more gravity. Right? More, can I say force in there? More force of gravity. So one thing that we can write is we write F is proportional to M. And that should make sense, right? So the bigger something is, the more attracted you are to it gravitationally. Okay, now no jokes here about, never mind. Now let's talk about the other thing that matters. And that is distance. Alright, I just told you that the more mass you have, the more gravity you have. Well, here's the Earth. We'll put E for Earth. And here's the Sun. Sun. Oops. Oh well. Alright, now you're, between the Earth and the Sun, as long as it's daytime right now. Now, the Sun has way more mass than the Earth does. It has, let me check my chart here. It's got, not quite 1 million, but it's well over 1,000. It's on the close to 1 million, 1/3 of 1 million, right? So that'd be 300,000 times as big as the Earth is, for kilogram-wise. So why aren't you pulled off of the surface of the Earth and ripped into the flaming abyss of the Sun because of its increased mass? So it should have more gravity, right? Well, you say, I'm not, because I'm closer to the Earth, right? This distance is way smaller than this distance, even based off of the picture. So what do we know? We know that the more distance is equal to less gravity. Okay, so what we can write, if we do this mathematically, is F is proportional to 1 over, now for distance, we don't use D, we use R for like radius between them, okay? Ta-da! Now, I do have one special caveat here. It's going to be R squared. Now, you wouldn't know that just from our conceptual example here, but you'd measure it from experiments and you'd know that it's a square instead of just a 1 over R. But that's not important. So let's talk about the formula. What's the formula? Well, we know that force is proportional to mass, and force is proportional to 1 over radius squared. So that means that force is proportional to mass over radius squared, right? Ta-da! Now, there's two objects here, so we're going to have two m's as well. Okie dokie. right? Because if you have more mass, then you are going to pull the other thing in just as much, so it's kind of symmetrical, whatever. Now, whenever you have things that are proportional like this, that means you can just throw in a constant and you're done. All right, so F is going to equal, this is a hard equal sign now, a constant times m1, m2 over r squared. And this is the formula. So let's talk about the newcomer first. So this is the universal gravitational constant. Gravitational constant. So fun. Okay, now it's got the word constant in there, and it's got this hoity-toity title, which means it'll always, always, always be the same forever. So this is going to be 6.67 times 10 to the negative 11. All right, that is the number that this is. Now it does have some units. We'll come back to that in a second because I don't remember what the units are, but I can figure them out. And I'll show you how you should be able to figure them out. So let's talk about these guys. Both of these are mass. Both of them are going to be in kilograms, right? Now, the masses are the two things. So, for example, the Earth and the Sun, the Moon and the Earth, whatever two things you're talking about, right? R is the distance between them, or radius between them. All right, that's going to be in meters. Ta-da! And F is going to be the force of attraction. It's always going to be attracting. Right, and that's going to be in newtons. Now remember, a newton is a kilogram meter per second squared. So, I've got kilograms. I've got two of them right here. Okay, and I've got 2 meters down here because it's squared. So what are the units for this have to be? Well, I need seconds, so I'm going to put seconds squared in the denominator. Now, meters has to end up on top, so I have to cancel out these ones and put more on the up there. So it's going to be meters 3. And then I also have to put a kilograms in the denominator to cancel out one of these kilograms, so I'm only left with a single one. And that's the units for the constant. Do you have to memorize the units? No. Why? I don't memorize the units, as I told you a second ago, and I don't remember what it is. But you should be able to reinvent it if you know the formula. This is, once again, a formula that's on your formula sheet, along with all the ones we've done so far, except the range formula. But you don't need the range formula. Anyways, whatever. So, this constant is also on your formula sheet. I'd show you where, but I can't because I'm inside your box of a phone / computer. Okay, well, maybe if you ever come back, I'll show you. Let's do a practice. What's the force of attraction between the sun and the earth? Now, for here, because subscripts are a pain, for me, I just used a big M and a little m. The big M is for the thing in the middle. In this case, it's the sun. Now, I hope that doesn't confuse you because the sun is way more massive than the earth is. Alright, so those are the two masses, and that's the radius between them. I have a handy-dandy planet sheet that I printed out because I don't like looking these up. You don't have to memorize these values at all. Normally, I'd have them on the board, so that way we can use them without me having to write them out each time, but I guess those luxuries have passed. So, to find the force of attraction, F is equal to big G, m1, m2, over r squared. So big G is 6.67 times 10 to the negative 11, times m1 is going to be 2 times 10 to the 30, times 6 times 10 to the 24. I did round these ones slightly because, you know, make it easier. 1.5 times 10 to the 11. Don't forget the squared. Ta-da. Alright, now we just got to type this into the calculator. Please make sure you actually type it in your calculator so that you know how to type this complicated formula into your calculator. 6.67 E, remember the E button, times 10 to the minus 11. You're going to get familiar with it real quick. Times 2 times 6 times 10 to the, oh, let's cheat a little bit for me. 1.5 times 10 to the 11 squared. Okay, now if you type it, I'm not going to say that because I don't want to confuse you. All right, so all this is equal to 3.56 times 10 to the 22 newtons. Hey, that's a big force. Yes, it is a big force, but you're moving the planet, so you know that's kind of what you need. All right, I think we got one more in here. Alright, if you are 70 kilograms, how close to your neighbor do you need to be to attract them as much as the sun? Alright, so do we understand the situation here? So here's your neighbor, here's you. Alright, so we're looking for what's this distance got to be, call it D, to attract it as much as the sun. Remember, it's not a sun if it's not wearing sunglasses. Alright, so we know what this radius is, so give or take. Alrighty, so see if you can figure this out. Go for it. Pause the video. Alright, did you finish yet? Alright, so force of the sun is equal to force of you. So force of the sun is going to equal G times mass sun times mass of friend. Can I just use little m for that? Divided by 1.5 times 10 to the 15. 15? I thought it was 11. It should be 11. Oh, sorry if you did it already. Anyways. Squared is equal to force for you is going to be G times the mass of you, which is 70, times the mass of your friend, divided by D squared, because we're solving for D. Alright, you could have called it R, who cares? Alright, something you should notice is the G's cancel out. G's. Also, the mass of your friend cancels out because it does not matter for this situation. Alright, solving for D squared. So D squared is going to equal, let's see, I'm going to have a 70 over here. I'm going to have a 1.5 times 10 to the 11 squared, and I'm going to be dividing this by the mass of the sun, which is 2 times 10 to the 30. Alright, I think that's all the numbers, yeah. Cool, so calculator, typity time, 70 times 1.5 times 10 to the 11, squared, divided by 2 times 10 to the 30, enter to the square root. Alright, so D is going to equal 8.87 times 10 to the minus 4. Alright, so let's see, that's going to be 8 meters. Alright, so that's going to be 0.8 millimeters. Just so that you have a point of reference here. Now, of course, you'd never actually do this because you're supposed to be socially distancing and all of that. Alright, hopefully you had fun with gravity today. We'll see you tomorrow.